everybody else can get to blink too if it's wrong. Okay. Ilias Sadek. Ilias, we don't see your face, but we see your slides, but that's maybe because you're not speaking, so your face doesn't come up. There you are. Yeah, we got you. Yeah, Ilias on the overlap gap problem. And I don't quite know exactly what time it is here, but if you want to take 25 minutes from now, go for it. Take it away.
Sounds good. Okay, let's see if the slides are working and stuff. Okay, everyone, thanks a lot for the invitation, and I hope to see you soon when I visit Simons in a month. So I will talk about the overlap property in inference. I will attempt in this short talk to make a short survey. It is a little bit optimistic, but we will see how it will go. Okay, so overlap property in inference. Let's start. So introduction. I mean, okay, not big news, and Salil made a very good introduction for this. Like also, like computational gaps and trade-offs appear quite frequently in random environments. That's something we'll know, and we all do research about here. And you know, at least for me, if I have to classify like which type of search problems at least admit these computational trade-offs, I will do this by classifying them in two roughly main categories. So first of all, I would say that there is like these optimization problems. So these optimization problems where there exists this, if you want, random function that we're trying to minimize, and you know, like let's say subject to beta belonging in some configuration space or some physical region. And you know, example of this is of course the springless Hamiltonians, like the maxat problem, maximum dependent random graphs, etc., etc. And what is a gap? A gap is the phenomenon in optimization where when we try to do this optimization in an efficient way, and efficient means polynomial time from now on, we get stuck. So like we see the phenomenon that all efficient methods get stuck away from the optimum, let's say multiplicative factor 1 plus alpha away for some alpha positive. And the question is why? Why like this gets stuck? Another category is of course the topic of the semester in Simons, where like, you know, it's inference or estimation, where we're observing a data structure that is sampled from a certain parametric distribution, and the parameter is the signal, and the goal is to use the dataset to infer the signal. Associated usually with this, as we saw in the example that Celine described, like there's a certain signal to noise ratio usually that really tries to quantify the intensity of the signal in the data structure as compared to the noise. If you want, in some examples, you know, this is like the sample size. So how many samples do you have? Some other examples, for example, in the planted click, this is like the size of the hidden click. And you know, some examples: planted click, generalized linear models, sparse regression, and principal component analysis. And you know, what's a gap here? A gap takes the following form, which is a little bit different than optimization. There exists usually information theoretic signal noise ratio lambda 1, above of which we know for lambda bigger than lambda 1 we can make the inference. Yet oral efficient algorithms will be getting stuck at some lambda 2, which is strictly bigger than lambda 1. And this is a gap. The question is why? Why we need this extra SNR to make this by efficient algorithm? And what overlap property is about is a part of a much more general scheme, a much more general field that tries to explain these gaps, to make sense of these gaps through geometry, through possibly some associated with this certain geometrical phase transitions, at the hope that like this will, you know, make some sense out of it. Okay, so let's see OGP for optimization real quick in one slide, which is, to my understanding, has been discussed already substantially already in the semester and also in the bootcamp in a bunch of talks. So I will not go much more into it. I will focus on the other one. But let's see a little bit more, like for the people that haven't been there or haven't seen, like what it is. So in this case, you know, there exists a random function. Let's say that like the feasible region is a subset of the sphere in p dimensions, and the efficient algorithm seems to be getting stuck 1 plus alpha away, some multiplicative factor away from the optimum, which is bigger than 1. Okay, what does geometry have to do with this? So, okay, this goes back in statistical physics many decades, but has been very nicely phrased, for example, by Aklotas and Kozaklan in 2008. It's this observation that between the regime that we can do the optimization efficiently and the regime that we cannot, easy I mean when you can and hard when you cannot, or excuse me, with conjecture you cannot, like it seems you cannot, then there is actually an abrupt change in the geometry of the space of near optimal solutions. In other words, there's a geometrical phase transition that's happening between the easy regime and the hard regime. We observe this to be the case in many such problems. Or in other words, if you want, there exists a certain property, a certain geometrical property that seems to be appearing in the hard regime, possibly blocking the efficient algorithms from working, which disappears in the easy regime. So people were trying to understand like what these properties, and there is some very, very beautiful works all around. For example, like about the Saturn property, other types of properties like Saturn property, condensation property, frozen variables property, various forms of replica symmetry breaking, and you know this more strict and recent notion of overlap property. Focusing on the latter, what is the OGP? So the OGP has been initially defined by David Kamani and Madhu Sudan in 2014, at least in this form. And it's the following idea. Okay, so let's say that you want to find an efficient algorithm that tries to enter this region 1 plus epsilon opt. So tries to find a beta that has a value of beta at most 1 plus epsilon opt. Then what's the OGP prediction of when you can do it or not? It tells you, okay, take this epsilon, so epsilon is some positive number, take this epsilon and consider this following set. Take all beta and beta prime that have value at most 1 plus epsilon opt, so this is the beta and beta prime you wish to find, and take all the possible distances between them. Okay, so because we're in the sphere, this is equivalent with taking all the possible dot products between them, or the overlaps between them. And then the idea is somehow to measure all these possible distances between them, all the possible overlaps between them, and then check if it's an interval or not. So what's the conjecture? The conjecture is that efficient optimization, you will be able to enter this near optimal region 1 plus epsilon away in an algorithmically easy way, if and only if tau sub epsilon is actually an interval, or not close to being an interval. And let's put this a little bit into context. By Cauchy-Schwarz, always like these overlaps are inside the -1, 1, because we're on the sphere, and 1 is always inside the tau sub epsilon, of course, because beta equal beta prime for some near optimal beta can be chosen. And the question is this like an interval, or there exists like this bunch of other intervals as well in tau sub epsilon, and in particular, there exists this prohibited overlaps. Where in the latter case, we say overlap property exists and we believe the problem is hard. If it's not this the case and it's an interval, we believe the problem exists. And of course, like at the conjectural level. Now, what's nice about it is that actually a multi-dimensional version of this that I don't want to bother you about. It has been proven to actually be the case. For example, the maximum independence set problem, or recently by Guy and Bryce in the random case that we're going to hear in this workshop by Bryce. And what's also nice about it is that OGP for optimization has the nice effect that it actually rigorously implies the failure of a large family of algorithms, in particular, which called stable algorithms, which in particular contain the low degree algorithms. So these are kind of the attractive notions of OGP for optimization. This talk now will be about OGP for inference, so I will make an attempt to serve this as well, that we will see actually it's a little bit different. So it's like, even if it looks like and it's motivated for OGP for optimization, it needs to take account, or at least it does take account at the moment, a little bit of a different route, which we can discuss if it's necessary or not. So then, I will try to do a definition and an overview, and then, okay, hopefully I will do 2 case studies in a very high level. I will show you how to apply this fuzz regression and the plan-click case. Sparse regression will be easier, plan-click will be more involved, but nevertheless, it unravels, I think, some structure we didn't know about the plan-click model. Okay, cool. So let me start. Okay, OGP for inference. So what's the setting here? So it's not optimization. So we have a data set here, sample for some parametric distribution, and the parameter is the signal that belongs to some parameter space that we assume again for simplicity is a subset of the sphere. So unit norm. Cool. What does geometry have to do with inference? So the jump is a little bit, let's say further than in optimization. But the idea is somehow that a lot of times to do inference, you do optimization. So a lot of time to do inference, what you do is you decide on a loss function you really believe in, let's say the empirical risk or something like this, or like minus the likelihood. And what you do is you try to minimize it. And you minimize it over all the beta in your or your parameter space. And the goal is ideally that somehow this loss is informative enough so that if you actually minimize it, you recover beta star. So you recover the true signal. And this is the loss we'll be using the data set in some way. And this is just to remind us that the beta star is generating the data set. Okay, so usually you associate certain informative loss functions that if you minimize, you actually recover beta star. So of course, immediately that puts us in information theoretically relevant regime, but this is a good assumption, I think, of course, for algorithms. So the question is, maybe by studying their geometries, these geometries, we will be able to say something. Now, there's a certain belief here to define OGP, at least the way we did it, and there's a certain belief that somehow there exists this canonical loss function, or if you're on the family of canonical loss function, but let's say canonical loss function, think in your mind that's the likelihood. So like there exists this standard loss function that actually the landscape of it really captures the hardness of the inference. So somehow there exists this canonical loss function that if you minimize it efficiently, you will recover beta star. And somehow if you recover beta star, this is what you should be minimizing. So somehow this is the belief that somehow there exists this canonical loss function that really it captures the hardness somehow. And what we believe back then, and I think it's when we defined it, it was that the answer is the likelihood. But we will see in the plan-click taught us that actually it's not as easy, but nevertheless not that far. Like a proxy of the likelihood should work. Okay, so if you believe this and you have this canonical loss function you really believe in, then what you should do is the following. So, okay, so you have an optimization problem that you want to study the landscape. Now, the truth is now the data set is not pure noise. So it's not like optimization. So somehow there is a certain hidden signal that puts a slope in the landscape. So everything leans towards beta star, which is the optimal solution. So what we decide to do is the following. We define the overlap probability for inference with David Kamani in 2017 to be the following form. Take any near optimal beta in this informative loss function, which is away from the optimum, let's say by slack R. So fix an R and take all the R near optimal solutions. And now do not take pairs of them, etc., etc. Just take any such near optimal solution and measure the angle it has with beta star, the distance it has with beta star, and measures all the possible distances it has with beta star. And the idea is that somehow, because the landscape is skewed towards beta star, maybe projecting along this line will have enough geometry, enough essence. The geometrical bottlenecks will be captured even in this projection. And our projection is the following: that somehow, if you construct these sets for all R, then the optimization problem with the canonical loss function will be easy, and based on the belief, the inference will be easy, if and only if this tau sub R is actually an interval for all R positive. So somehow, for all near optimal regions, if you cut there and take the near optimal betas and you measure the angles, if they are always an interval, then we believe inference is easy. But if there is this near optimal region that if you cut, you see these connections and bottlenecks, we believe the problem is hard. Okay, and think I'll use your mind loss as the likelihood to make some sense. So before continuing, I just want to tell you that like these losses have been applied in different contexts, and okay, it's slightly different versions, but most morally, like I would say, it looks like this. In different ways, I will try to talk a little bit about this too, but if you're interested, one of the others, like come talk to me or come to talk to the authors that I'm sure are around in Simons. Okay, let me continue. So let me a little bit give some mathematical intuition about this overlap approach for inference. So, okay, because I think it may make sense, maybe not, but like somehow it's a little bit complicated of how to approach proving the logic for inference exists or not. So there's a nice equivalent definition with spectrum monotonicity of a certain curve. So imagine the following situation where you define this following random function that takes an input a zeta, which we will say will be the overlap with beta star, and outputs the minimum possible loss value of this canonical loss function that, of course, takes among all parameters, so all beta or signals, beta or possible signals, beta in the parameter space, that have a specific overlap with beta star. The specific overlap. So the angle with beta star is zeta. So for any zeta, tell me the best possible loss value that you can achieve with this angle with beta star. Okay, of course, this is purely for analysis purpose, right? There's no optimization you can actually do in practice or when you try to solve the problem, just for the analysis purpose. So to consider this random function, okay, let's try to make a little bit of sense of this. If zeta equal 1, this is only beta equal beta star, of course, by Cauchy-Schwarz. So like, what I'm telling you here is for zeta equal 1, give me the loss value associated with beta star, which as I told you will be the minimum. So how gamma is clearly minimized at 1. When z equals 0, this is like all the orthogonal, all like the junk, if you want, with respect to inference. So there's a nice lemma that actually overlap probability for inference is actually equivalent with this gamma being non-monotonic. So like if the gamma is non-monotonic, then there is overlap probability for inference and vice versa. And what's the idea here is like, this function is always minimized at 1. So the question is this like actually decreasing? Or is it like at some point increasing then decreasing? Of course, it can increase and decrease many times, but somehow let's assume for simplicity this is the case. And you can see one direction, for example, like it's really not a hard situation. So if it's increasing and then decreasing, then you can always cut the hill in the middle here. And if you cut the hill in the middle here, what happens is that you can consider R to be the slack to optimality from this red line, horizontal line. And if you consider all the near optimal betas that achieve this value, what happens? If you consider any zeta here and any beta with this overlap, the best loss value associated with this overlap is above this line. So all of them are excluded. And of course, because the curve is below here, these are included, so in particular, there is also included. So indeed, like, this monotonicity translation and other direction is similarly. Okay, and this is actually kind of nice because, it gives you a concrete mathematical task, but also, it's worth mentioning that this is not as easy maybe as it seems, to the extent like usually indeed, even if it's a concrete mathematical task, the analysis of this is challenging because, you have not only to understand the first order behavior concentration, let's say, of this random function for input zeta, you need to understand how it compares with the other zeta. So somehow you need to understand second order information, which is challenging and requires like actually, a heavy concentration analysis of the zeta function, but nevertheless is a concrete task. And usually, we go about it, at least I have been involved in projects that we go about it with the first and the second moment method. The first moment method usually gives you, a lower bound on this restrict optimization random function, which is a deterministic lower bound. And second moment method usually tries to prove the tightness on it. But a lot of times, even if you take the first moment lower bound, it's a deterministic curve, you can analyze the monotonicity of this deterministic function and get predictions. Even if you haven't proved the tightness, which of course you formally need to do to use the lemma and prove the OGP. Okay, so hopefully this makes sense. This was the definition of the overview, and now I can jump into some case studies. Again, so how do you apply OGP for inference? You decide on a loss function that you really believe in, and that's the belief. And then what you do is you study the non-monotonicity of the associated restrict optimization curve. If it's non-monotonic, we believe it's hard. If it's monotonic, we believe it's easy. Okay, so let's jump into sparse regression. So this is the first example that we apply this. So in sparse regression or compressed sense glitch, let's consider a simple model. So there exists a signal here for us, it's just a binary k-sparse vector. Okay. And let's assume X here, it just has ID standard Gaussian entries, and the noise has ID mean zero and various sigma square entries. And what happens is we make n noise linear observations of this vector beta star that we put in a vector form, but nevertheless, let's write here like this. So it's the projection, the noisy projection along xi of the signal, and you do this like n times IID. And the goal is, given y and x, given all these observations, like, can you recover beta star? And you're going to do this SNR here is the sample size. So somehow you're going to do this with the minimum sample size possible. Okay, so what's going on with this model? This model has been studied, to death in some way. So like there has been like a lot of works. I mean, in specific parametric regime, what happens is the following. So if the sample size is above some critical sample size null, then this is actually where, if that means anything to you, restrict the isometry property appears for the matrix X. Actually, Lasso works, or like, which is a high-dimensional statistics algorithm, a convex relaxation method, or like some compressing methods like automatic should work. On the other hand, information theoretically, actually in this regime, you can go lower. You can go actually in a different order of magnitude, which is n star, which is another sample size, which is below it, actually, you can prove it's impossible, and above it's possible by the MLE, actually, let's say, but it's in principle not volume and time, and, question marks until you reach the null. So we said, okay, maybe this is a good candidate to apply this model. So good. So we need to understand two things, right? Loss function and monotonicity. So like to understand the OGP. So what's a loss function? I mean, the good candidate always the likelihood. So the likelihood the landscape makes sense. So like it should be like some canonical thing. And what's the likelihood here? Because we have Gaussian additive noise, which is just white. I mean, this is just least squares. So the maximum likelihood turns out to be just least squares, of course, over your parameter space. So overall, the beta k-sparse vectors, binary k-sparse vectors, you want to minimize the least square error between y and x beta. And you can ask, okay, is this informative, as I said, to use my terminology, like is the minimum indeed at beta star all the way to the IT threshold here? It is. So like there is a result, I mean, that you can prove that actually, like it reaches this. So like the minimum here is beta star. It is an informative loss function. And naturally you can say, okay, perfect. So let's understand this landscape. Like, is the OGP prediction accurate for this landscape? Okay, as I told you, you need to consider the restrict optimization curve, which fix an angle with beta star, the signal, and tells you how small can you make the least squares error if you overlap that much with beta star. And if it's non-monotonic, we believe if it's non-monotonic, there is OGP according to our definition, and we believe that the problem is hard. If it's monotonic and decreasing, then we believe there is no OGP, and the problem is easy. And turns out actually that this is the case. So with David, we proved in 2017 that actually in the polylogarithmic regime for K, up to constants, we're losing constant control, like because of the second moment method. Like somehow, like indeed, this is the phase transition. So like if you are up to constants in the hard regime, then with high probability gamma is non-monotonic. So indeed it has a bump, and there is overlap property. And if n is bigger than CNR, then with high probability gamma is monotonic, and there is no overlap property. It is very nice because it has nothing to do with Lasso, it has nothing to do with OMP. It's just like a prediction that like we build based on these other physics conjectures. And indeed, it seems to be coinciding with the failure of convex relaxation compression methods. So indeed, like that was a success. I would say. Okay, now let's start getting things a little bit more complicated with the planted click model, unless, there are questions, of course. Okay, cool. So planted click model. So the situation is a little bit different here. So let's remember what's the planted click model. So there exists N and K, so two parameters. So first of all, how do you create an instance of the planted click? You sample a GN_half. So for n equals 7, you're here. So okay, what do you do for the GN_half? You choose n vertices, and then for each pair of the vertices, you flip a coin independently with probability half, and you place the edge on. So for n equals 7, let's say you create this thing. Then in the second step, you choose k out of the n vertices uniformly at random, and you make it a click. So if some edge was not appearing, you force it to be there. So here, for k equal 3, you may happen to decide these vertices and you make it a triangle. And the planted click inverse problem is given access to this, of course, without the colors, is like you want to recover the planted click. And the goal is, for how small click size can you actually recover? So, if the k is super large, possibly, it's evident what's the planted click. If k is super small, possibly it's not. And another problem has been starting to death, and we really understand, at least at this level of the information theoretic world, but also many algorithms, we understand, for example, that, the phase transition happens at 2 log with base 2n, that below, we know that actually it's impossible to recover, and above, actually, it's a unique k click in this planted click instance. And yet, we can, because it's a unique k click, let me elaborate, you can search of k vertex subgraphs and check if it's a click or not, and this will give you a non-polynomial time algorithm, actually, that works, a quasi-polynomial time, but nevertheless it works, which is non-polynomial, and yet, if you ask for polynomial time, you need to enter the square root 10 regime. So you need the click size to be square root 10. And then we have spectral NP methods and other methods as well. Okay, so we said perfect, that's another candidate. So the first issue is, somebody will say, let's try now the likelihood again. Likelihood and monotonicity. The problem is that actually this Boolean problem has actually a likelihood which is degenerate. So if you study the likelihood or the equivalent, the posterior of the planted click problem, then for any C which is a subset of a vertex set which has cardinality K, the probability that C actually corresponds to the planted click vertices given G is really proportional to the indicator that C is a K click, or induces, if you want more correctly, a K click in G, which is pretty bad. So because there is a unique K click all the way here, what happens, the posterior is 0 everywhere, and it's 1 on the planted click vertices, which is why I'm saying all the time it's bad. It's because there is no notion of near optimal solution. So OGP is not applicable. There is no notion of, okay, my likelihood is near optimal. It's either 0 or 1. So this is the first bottleneck, and what we decided to do then was maybe we should take a proxy of it. So maybe what we should do is we should study the dense subgraph problem, which is actually the likelihood of if you plan a dense subgraph and not a click, and also it's a natural proxy of what it means to be a click or not. So what you can do is you minimize over the k vertex subgraphs the loss function, which tells you how far away are you from the click, how many edges do you miss to be in a click. Equivalent, this is of course maximum of this. So the dense subgraph problem, the k dense subgraph problem, to be more specific. Turns out actually that even this has issues that I'm going to explain, which I think go deeply in the planted click understanding. And nevertheless, what's the right thing to do is actually what you need to do is study the k bar dense subgraph. So you should study actually the k dense subgraph problem for the k bar dense subgraph problem for k bar which is larger than k. So you need, if you want to lift. So you want to look at what happens at the k bar vertex subgraphs, where the click remains of size k, but you need to lift and to study the landscape above it. And let me elaborate of why on this for a moment. So I tell you, actually, this family of optimization problems is what you should be studying after you lift the vertex size. And how do you study this? Okay, again, you need to study, of course, the OGP, so the restrict optimization curve, which tells you if you overlap that much with the planted click, how dense can you make it, but being a k bar subgraph, and check the monotonicity. So I will not describe what's going on for the second moment here because it's actually very complicated, but I will discuss what happened with respect to the first moment estimation. So if you just take the first moment estimate and do the analysis, which is already complicated, of what the prediction is, the following, I think, interesting phase diagram arises. Okay, so what's going on here? Let's try to make sense of it. Here, this is the planted click size. So this is, vanilla and what the planted click size is. This is actually, if you want, the algorithm's designer option. So it chooses which k bar, which landscape it needs to study here. So which vertex size you want to study. So there are actually 3 regimes that arise. If k is less than square root n, if you choose a k bar, a vertex size for the dense subgraph problem, which is above k, so this is the line, this is what naively you would be doing if I didn't tell you to over-parameterize. But I tell you now to look, to lift and see the whole picture. So if k bar is bigger than k, then actually there is OGP. So we predict the problem is hard. This dense subgraph problem, cannot be optimized efficiently. But yet if you lift, actually you lift the OGP, which is nice, the local barrier is erased, but somehow the curve becomes monotonic in the wrong direction. So somehow it's completely uninformative. The optimal solution is completely uninformative. If k is between square root n and n to the 2/3, it's still hard, actually, if you are around k bar equal k. But nevertheless, the problem becomes easy and informative. There's a sweet spot where the problem becomes easy and informative, which agrees with the intuition that square root n is the transition point. And if k is above this weird n to the 2/3 transition, actually it's immediately easy and informative. Okay, this can go for a long way to discuss about this, but what I want to say is, if you only focus on this, you see this n to the 2/3 bizarre transition, which is, there will be actually, there was some follow-up work that Maria Cariangelini will talk on Wednesday about it, also the importance of over-parameterization for local methods where OGP tries to capture. And also I want to mention, that, at square root n, there is an OGP phase transition, but somehow a very different one when you need to lift. Okay, and let me wrap this up. Also, I want to mention that this actually agrees with algorithms. So if you try to do greedy local search in these landscapes, even with simulations or even with analytic arguments, you will see actually that there is importance to lift, which I don't understand other than algebraic reasons, honestly. So there is some importance here to lift that we were missing. And let me wrap up. So there's another direction also for OGP for reference. I didn't have the time to talk, but I think it's very interesting that somehow OGP for reference allows you to prove refutation of MCFC methods, and actually can give you even some exponential time predictions, if that means anything to you, that agrees with the low degree method. Okay, so cool. So OGP for inference gives valid hardness predictions. There is an issue of what's the optimal loss function. It seems to be more complicated than we expected, for example, in the Planet-Cliff model. And two main questions about what would be, I think, ideal to be proven for OGP for inference that we don't yet understand. It would be very nice to prove refutation of a much larger class of algorithms based on OGP for inference beyond MCMC, like, for example, stable algorithms. And also, I have some belief that maybe the absence of OGP can be leveraged by algorithms and to prove success of local methods for inference, similar to, for example, what happened recently in the spin class theory for the no OGP there. And I will stop here. Sorry for taking a few more minutes. Thank you.
Okay, so because I don't want to deny people snacks any longer, I think we'll do the same thing as we did for Greg's talk, which is that I'm going to leave this mic up at the podium. It has an on-off switch. Please use it to ask Ilias questions, but we're going to go ahead and release people to the reception, which is outside. Thank you all for being here. We'll see you tomorrow morning. Are there other examples where this over-parameterization thing needs to happen? Or do you conjecture other, it's pretty strange.
Yeah, it's super strange. I mean, I don't know. I mean, my guess would be that this could be a solution for issues like the tensor PCA model that we know the local algorithms are suboptimal. But maybe it could be the case that somehow we are just missing the appropriate lifting of them. So somehow, I would expect, for example, a simpler problem will be the sparse PCA that's a little described. That maybe it could be the case that somehow appropriate lifting we're missing. But,
let me say that there's a bunch of people here to ask you questions, so I'm going to hand off the mic. Sururato is here first.
Hi, Ilias. Thanks so much for the talk. Sorry, maybe I can just ask you a bit about your last question. So, for these planted problems, usually, if I pick a sample from the posterior and I look at its overlap with the planted truth, then it's usually a constant, right? So, then.
Can you repeat? So, brother, I cannot hear very well.
Oh, sorry. Is this better?
Yeah.
Okay, yeah, no, sorry. I'm just wondering that if I take a Bayesian posterior or something, right? And if I look at the overlap between a sample from the posterior and the planted truth, then it's usually concentrated at a fixed point, right? So in this case, what do we mean by the absence of OGP?
I mean, I don't like this connection. What do you mean? So if you sample from the posterior and what's the intersection you say the signal that will be constant? Okay, I think I understand what you mean. So So usually the OGP for inference, what I didn't say is this non-monotonicity happens at the somehow the transition happens at the low overlaps, not at the constant level. Somehow, even if, like the optimal thing.
I see. It's like you mean that one has to look at the part near the like random initialization, and if you have like, oh yeah, okay, I understand. Yeah. It's sort of what we see also for this like planted like matrix with higher means. I understand. Okay.
Exactly. That somehow it's okay. I would say the derivative at zero is a good candidate.
Yeah. Okay. That makes sense. Thanks so much. Yeah, I guess I'll pass it on to Bryce.
Hi, Vince. Thanks for the great talk. My question is about the n to the 2/3 phase transition in Planet Clique. So the landscape is easily beyond above n to the 2/3. So does this mean you can like find the Planet Clique by some sort of like iterated Markov chain where you first use a Markov chain to find a set of n to the 2/3 vertices containing the Planet Clique, and then now restricted that as a new problem instance, and then do it again and somehow eventually find the Planet Clique that way?
It would morally mean this for sure. I mean, we have an algorithm that looks like this that works. What relates a little bit is this C thing I was mentioning, that somehow we do not know a way to turn directly the OGP to a success. So but for similar reasons, let's say, with the absence of OGP, we can prove the success of a local method. That looks like this. But what is interesting is below the n to 3rds, if you do the same thing in the shape, then actually it works. But it doesn't work if you don't know what to do.
I'm sorry, your audio cut out for a second. Can you say that again?
Sure. So what I'm saying is that in above the n to 3rds, like if you do what you just described, or even a more basic version of what you said, it works, as you said. But what is interesting is even below the n to 3rds, it doesn't work. But if you lift, it works.
Yes.
So like that's what I'm saying. Yeah.
Yes. Can I chime in? Can you hear me, Bryce and Elias? Can you hear me?
Yes.
Yeah. So I think a related interesting question about n to the 2/3 is that actually the Markov chain is slow. When you do the Markov chain on the in a non-overparameterized regime. So you do the random walk on k-side sets, and it's conjecture, which is sort of evidence of this conjecture overlap gap property, that it will be slowly mixing, which would be quite interesting because originally Jerome, when he introduced the planted clique model, he called it a difficult problem because it's slowly mixing in the regime below square root n.
Yeah.
But it might be still slowly mixing even above square root n, even though, so his conjecture was absolutely correct. But evidence might be wrong.
Sorry, David, did you say that above n to the 2/3 Markov chains are fast?
No,
No.
I would imagine probably yes. But below n to the 2/3, Markov chain is.
Yeah, there's so much noise from the room. Yeah.
Elias, great talk.
Oh, you like them? That's good.
I'm just editing noise. I want a signal.
Yes, I mean it's like there's so much Bryce. There is so.
Thanks so much.
Yeah.
Hello, hi, Elias. This is Jiaming. Hi, Eric. Can you hear me?
So far, at least, yeah.
Oh, okay. Sorry. Yeah, I just have a quick question about the Planet Clique example. So there, I understand like you only have the unique k-clique, but then you know like to find the Planet Clique, you only need to find like 3 log n size clique, right?
Yeah, absolutely.
So in that sense, can I study the problem that instead of looking at approximation of k-clique, you look at approximation of 3 size like log like 3 log n click times 1 minus epsilon, then you probably have many clicks, and then you can study the overlap.
Yeah. So this is a good point. I mean, I haven't. I don't know. We haven't. I haven't done this, and I don't know. We didn't do this. I mean, it's. I have checked. I think back in the day, and there was a similar OGP kind of appearing there as well. Like, but we never like actually completed these calculations. But I think you make a good point that somehow, if you find like this 3 log n click, you can always expand it to the planned click, and this is where actually. Yeah. Actually, now it's been some years. Now you're reminding me exactly like what is the long short answer is yes, and I think that like I have checked some first moment calculations, and they seem to be suggesting the same transition with respect to the same transition, at least that like until root 10, if I remember well, there was OGP. I don't remember above root 10. But I think you're very much right, and actually this is a direction that can capture the quasi-polynomial aspect of it. That our work does not, for example. Yeah.
Okay. Yeah. Thanks. Yeah. Just want to clarify that.
Yeah. You're right.
Okay. It seems like we're done with the question. We're going ahead to the recession. Okay. Yeah. Thanks a lot.
No, thanks a lot.
Yes.